Okay, answers for the free response questions. These are the real deal. This is 2002, number 4. You notice these are from the A-B test, but there's a lot of overlap. Usually 3 or 4 out of the 6 free response questions are the same on the A-B and the B-C test. So I don't remember in this year if it was the same or not, but could easily have been. Okay, so I've got this graph of the function f. It's not f prime, always important to note that. This is the f function. It goes up and down like this. And the g function is defined to be the area from 0 to x under this. And they would like us to find g of negative 1, g prime of negative 1, and g double prime of negative 1. So, let's see. G of negative 1 would be the area from 0 to negative 1. Right? That's how this function is defined. Excuse me. Under the f function. So let's see. The area from 0 to negative 1, that's a triangle that's 1 by 3. Right? So that'd be 3 halves. But this is a positive area, but the integral is running backwards. It's going from 0 to negative 1. So that makes that negative. So there's our first answer. G prime of negative 1. Well, what's the derivative of this function? The derivative of an integral function, it's just f of x, right? It cancels this out when we take the derivative. So that means that g prime of 1 is just equal to f of 1. Oh, sorry, negative 1. So g prime of negative 1 is just equal to f of negative 1, and f of negative 1 is 0. And then last, the second derivative of this, we're taking the derivative. So the second derivative of that would be the first derivative of this. So that means that g double prime of negative 1 is equal to f prime of negative 1. And that's the slope of this here. It looks like the slope of that is 3. Right, it's just a straight line. Okay. Part B. Find what values of x in the open interval from negative 2 to 2. For what values is g increasing? Well, g is increasing when the derivative of g is positive, right? That's how we find increasing and decreasing stuff. So, g prime is positive. Well, the derivative of the g function is just the f function. So saying you want g prime to be positive is the same as saying you want f to be, to be positive, right? So, like one way of interpreting this graph, this is the graph of f, but f is the same as g prime, right? So if you want g prime to be positive, well, that happens between negative 1 and 1. And this is absolutely fine for like explain your reasoning. This is an explanation. Part C. For what values is the graph of g concave down? Well, g is concave down when the second derivative is negative. And the second derivative of g is the same as the first derivative of f. Right? They're off by one derivative. So where is the derivative of this that we're looking at negative? Well, that's where the slopes of this are negative. That's right here. So that'd be from 0 to 2. And last, on the axes provided, sketch the graph of g on the closed interval. Well, what would g look like? Let's see. first of all, note that since this is defined from 0 to 0, g of 0 is equal to 0, right? This function goes through the origin. When you plug 0 in, you get 0. Now this, right here, that's the line y equals, has a slope of 3 and a y-intercept of 3. And over here, this is the line y equals negative 3x, same y-intercept, plus 3. Right? So, what's the antiderivative of this? If we're trying to find g, we're trying to find the antiderivative of this, right? So, on one side, g would be the antiderivative of this, which would be 3x squared over 2 plus 3x plus, I know it goes through the point 0, 0, so you could write plus c, but the c is going to come out to be 0, right, because it goes through the origin. And likewise over here, you've got g of x is equal to negative 3x squared over 2 plus 3x, and same thing, it goes through the origin, so the c is going to be 0. So what does that look like? Well, what does this piece of this parabola look like? Well, you could find, I mean, I don't know how much work we want to do about that, but you could find the vertex of this parabola and do some work like that. You can also look at this and say, if this is the derivative, this is a straight line, so we knew its antiderivative would be a parabola, right? Because this is just degree 1. And since this is the derivative, it looks like it's decreasing and then increasing. So this must be where the vertex is. It's at 1, right? And then we know it goes through 0. So it's, again, this is opening up. It's decreasing and then increasing. And if you plug negative 1 into this, you get, what, negative 3/2, something like that. So it looks like we have some piece of a parabola that goes like this. And then this is the mirror image upside down parabola. So this one is increasing and then decreasing. So this one looks like something like that. So it kind of looks cubic, but it's actually not cubic. It's two pieces of parabolas kind of grafted together. Do they come together with the same slope? They do indeed, right? The slope right there is 3 because their derivative is defined there. So they smoothly connect. All right, here's a similar problem. This time we're looking at a graph of the derivative of something. So that's a little bit different, right? Excuse me. Let f be a function defined on the closed interval from negative 3 to 4, and f of 0 is equal to 3. That's a point on the original function. The graph of f prime, the derivative of f, consists of one line segment and a semicircle, as shown above. They want to know on what intervals, if any, is f increasing, and justify your answer. Well, f is increasing when f prime is greater than 0. So we look here, where is f prime greater than 0? Only right here, from negative 3 to negative 2. Part B, find the x-coordinate of each point of inflection of the graph of f on the open interval from negative 3 to 4. Well, points of inflection happen where the second derivative goes from positive to negative or from negative to positive. Now we're looking at the derivative, right? So the second derivative would be the slopes of this. So the slope here is is all negative through here, and then it's positive here, and then negative here. So the points of inflection are at 0, and 2. And notice the points of inflection are the maximums and minimums of the derivative, right? Was it a problem that this had a sharp corner? No. The second derivative wouldn't exist here, but the definition of a point of inflection, it's not where the second derivative is 0, it's where it changes from concave down to concave up. So the second derivative does not necessarily have to be defined. Part C. Find an equation for the line tangent to the graph of f at the point 0, 3. Well, I've got the point 0, 3, which is actually the y-intercept, right? That means b equals 3. And now all I need is the slope. So to find the slope, I need f prime, the slope at 0. Well, I'm looking at a graph of the derivative. So f prime, that would be negative 2, right? This is the graph of the slopes. Slope is negative 2 at 0. So f prime of 0 is negative 2. So my equation is y equals negative 2x plus 3. And part D. Find f of negative 3 and f of 4. Well, let's see. If I want to find f values, I've got this, so I'm going to need to find the antiderivative. And I'm going to have to use a value that, the values that I know. The only value that I know in the function is that f of 0 is 3. So I need to make sure that I use the the 0, right? So I'm going to set up this integral. I'm interested in what f of negative 3 is, and I know what f of 0 is. So check out what happens here. What's the antiderivative of this derivative? Well, the antiderivative of a derivative is just the function, right? Those cancel each other out. So this is f of x from negative 3 to 0. So that's f of 0 minus f of negative 3. And since this is just like an area, I can find the area under this thing from negative 3 to 0 is just, let's see, that's this area. This triangle has an area of 1/2. This triangle has an area of 2, and that's negative, right? So that's 1/2 minus 2, or minus 3/2. So solving this equation, I know that f of 0 is 3 minus f of negative 3 is what we're trying to find, right? So that would give me, what is that, 6 and 9/2. So f of negative 3 is 9/2. Right? Likewise, you want to know f of 4? I'll do the work for that up here so you can see the picture. So I'll set up 0 to 4. Why am I picking 0? Because I know that value right there. So that's just f of x from 0 to 4, and that's just f of 4 minus f of 0, and I know f of 0 is 3, right? And also, the area from 0 to 4, just using geometry, I think you saw this graph before also, this is a 2 by 4 rectangle, so the area of that would be 8 minus half of a circle with radius 4, so that's, the area here would be 8 minus 2 pi. You can check that. So 8 minus 2 pi. And then I know that f of 0 is 3. So f of 4 is equal to 8 minus 2 pi plus 3. That's 11 minus 2 pi. So we used a picture and the really both fundamental theorems there to get that. On this page, I wanted you to do number 5, although we can do this one now too. We could do this one. A little bit more stuff in section 6-7 about that. I'll come back to that. This is the one I'm interested in. Okay, so f is a function. This is the graph of f defined on a closed interval. Graph of f consisting of 4 line segments is shown above. And g is another one of these area functions. It's the area from 2 to x, under this curve. So they want us first to find what's a g of 3. G of 3 would be the area from 2 to 3, plugging 3 in, the area from 2 to 3 here. That's trapezoid, or however you want to find that area. That's an area of 3. To make that calculation, but that's just the area from 2 to 3. The derivative of the g function, g prime of x, is just f of x, right? The 2 doesn't matter, remember. And that means that the second derivative would be the first derivative of that. So g prime of 3 would be f of 3, which is 2. Then the second derivative would be the slope of the f function here, and that has a slope of -2 at that spot. It's a lot like the first one. Find the average rate of change of g on the interval from 0 to 3. Well, average rate of change is a slope, right? So let me get some more paper here. That is just a slope. Average rate of change means they want us to do g of 3 minus g of 0 over 3 minus 0. It's the actual slope between those two. That's 3 on the bottom. So what's g of 3? We found that already. That's 3. And what's g of 0? G of 0 would be the area from 2 to 0. Notice that's backwards, from 2 to 0. So that's a 2 by 4 triangle, which has an area of 1/2 base times height, or an area of 4. But since I'm running it backwards, going from 2 to 0, instead of being 4, it's going to be -4. So that's minus -4. That's 7/3. Right? Super important that you understand average rate of change means a slope, actually using 2 points, not a derivative, an average rate. For how many values c, where c is in between 0 and 3, is g prime of c equal to the average rate found in part B? Ooh, this sounds like mean value theorem. So they want to know for how many values in between 0 and 3 is the derivative of the g function actually equal to the average rate. Well, the derivative of the g function is equal to the f function, right? We already established that earlier. Since this is an integral type function, the derivative of it is just that inside function. So what we're looking for here is, where is the derivative? Are there any c values in between 0 and 3 where the g prime is actually equal to 7/3, and g prime is just equal to the f function? So does the function cross 7/3 between 0 and 3? 7/3 is what, 2 1/3? So it looks like it crosses here and here. It looks like it does it twice. And we could actually find, these are straight lines, I guess we could find those values if we had to, but they're not asking. So twice. And again, this that would constitute the explain your reasoning. And then last part of this one, find the x-coordinate of each point of inflection of the graph of g, this interval. We just did this in the first one, or maybe one of the ones anyway, maybe the last one even. So, points of inflection, that's where the second derivative goes from positive to negative or negative to positive, right? And the second derivative of the g function is the derivative of this. So where does the derivative of this go from positive to negative or negative to positive? Well, here's positive to negative, negative, positive. So it looks like it happens here and here. Again, it's the maximums and minimums. Oh, wait a minute. Oh, I'm sorry. This is the graph of, oh, no, that's right. So the derivatives here, hold on. Let me check myself, make sure we're good here. We want the second derivative of this to go from positive to negative or negative to positive, which means we want the derivative of the f function to go from positive to negative to positive. Yeah, so that's correct. So it happens here at 2 and at 5. X equals 2 and x equals 5. All right. Last one, this graph should look familiar. You saw it somewhere in practice problems or the quiz from the 6163 stuff. We don't know how to do differential equations yet, so we're not looking at 5 here. We're looking at number 4. Okay, here's a graph of f. And we've got another g function that's defined in terms of the area from 6 to wherever, plus 5. All right, so let's see if we can find these. Try to make this so you can see everything here. Okay, so part A, let's find a g of 6. Well, g of 6 is equal to 5 plus the integral from 6 to 6 f of t dt. Well, area from 6 to 6 is just 0, so g of 6 is equal to 5. G prime of 6. Well, the derivative of the g function is the derivative of 5 is 0, and the derivative of an integral defined function is just the inside function, so that's f 6, and f of 6 is 3. Second derivative of the g function is equal to the first derivative of the f function, right? And f prime of 6, that's the slope here. It's got a horizontal tangent line there, so that would be 0. So 5, 3, and 0 for those. Okay, on what intervals is g decreasing? So g is decreasing when g prime is less than 0. And g prime is equal to the derivative of the g function is the f function, right? So where is the f function less than 0? Here and here. So from negative 3 to 0 and from 12 to 15. Right? Part C. On what intervals is the graph of g concave down? G is concave down when the second derivative of g, which is equal to the first derivative of f, is negative. So the derivative of f, that's the slopes of f. So where does this thing have negative slopes? Looks like it's got negative slopes all through here. So from 6 to 15. And last part. Find a trapezoidal approximation from -3 to 15 using 6 subintervals of length 3. You might have, I think we might have already done this, but I'll set it up anyway. That's not the reason I picked this problem for this, but we could do that. So each trapezoid is 3 wide over 2. There's 6 of them. The height of the first one is -1 plus 2 times, let's see, 0, 1, sorry, 3, 1, 0, and then the very last height is -1 again. Remember, those all get doubled, everything except first and last, because they get to be the left edge and right edge of 2 different trapezoids. So that's 1 times, that's 5 plus 2 is, getting late, 5 times 2 is 10, minus 2 is 8, divided by 2 is 4, times 3 is 12.